Hey everyone, and welcome. Today, we're putting on our lab coats and grabbing our magnifying glasses to solve a real chemical detective story. We're going to uncover a hidden secret inside a liquid you probably have at home, using a classic technique that's part science, part pure investigation. So let's get started. So think about this for a sec. That bottle of vinegar in your kitchen. You know it's acidic, right? That's what gives it that sharp taste. But how acidic is it really? This is the exact kind of puzzle that analytical chemistry was made to solve. We're hunting for a specific number, a precise concentration, and to find it, we need a plan.
And you bet that plan involves some pretty cool lab equipment. You see, chemists have this incredibly powerful and elegant method for this kind of investigation. It's a way to precisely measure something that's totally invisible and get the exact answer we're looking for. And believe it or not, it's been a cornerstone of chemistry for well over a century.
So that technique, it's called titration. Let's go ahead and open up the toolkit and see exactly how it works. Okay, so here's the textbook definition, but let's break it down. The key word to start with is quantitative. That just means we're getting a real number at the end, not just a guess. And the whole point is to find an unknown concentration. So at its heart, titration is just a super accurate method for figuring out exactly how much of something is dissolved in a liquid. It's all about careful measurement to uncover a hidden value.
And this is what the classic setup looks like. It's a pretty specific arrangement, right? That long glass tube up top is called a burette. It's basically a super precise measuring cylinder with a little valve at the bottom. And down below, you've got a flask, and that's where we put the mystery solution we're investigating.
Okay, so to really get a grip on this detective story, we've got to meet the main characters. In every single titration, there are 3 essential players that make the whole thing work. First up, we've got the analyte. This is our chemical of interest, the thing we're trying to figure out. It's sitting there in the flask at the bottom, and its concentration is the secret we're trying to uncover. So in our vinegar example, the analyte is the acetic acid. Next, we have the titrant. This is the stuff in the burette up top. And here's the key. We know its concentration with incredible accuracy. The titrant is our measuring stick, our standard. We add it super carefully, drop by drop, to see how our mystery analyte reacts. And finally, we have what I think is the most clever part of this whole setup, the indicator. This is our crucial signal. It's a special dye that we add to the mystery solution in the flask. At first, it just kind of hangs out, doesn't do much, but at the exact moment the reaction is finished, it dramatically changes color, basically screaming, "Stop, you're done, right here!" Now, it's not a one-size-fits-all kind of deal. Chemists have a whole toolbox of different indicators. Each one is designed to change color at a very specific pH level, which lets them pick the absolute perfect one to signal the end of whatever reaction they're running. And this right here, this is the magic moment. We're looking at an indicator called methyl orange. In an acidic solution, it's red. As you add a base, drip by drip, you hit this perfect, fleeting orange color. That's it. That's the endpoint. Add just one more tiny drop of base, and boom, it flips to yellow. That razor-sharp color change is the signal we've been waiting for. So the entire point of a titration is to nail this perfect balancing act. We're trying to find the exact point where the titrant has completely and totally reacted with our analyte. But there's a really subtle but super important difference between what's happening on a molecular level and what our eyes can actually see. Okay, so this is crucial to get. On one hand, you have the equivalence point. This is the theoretical ideal, the invisible moment when the chemistry is perfectly balanced. On the other hand, you have the end point. That's what we actually see in the lab, the instant the indicator changes color. In a perfect world, these two would happen at the exact same time. But in the real world, they're sometimes just a tiny bit off. The indicator might change color a fraction of a drop before or after that perfect chemical balance. That tiny difference is called the titration error. And let me tell you, minimizing this error is everything. We're not just talking about getting a good grade. In the real world, a big error could mean the wrong dose in a medicine or a dangerous level of a pollutant being missed in our water. So a skilled chemist's entire job is to choose the right indicator and be so precise that this error is practically zero. All right, so we've hit the brakes right at that color change. We've carefully recorded the exact volume of titrant we used. So now what? How do we take that one number and use it to finally crack the code and reveal the concentration of our analyte? Well, it all boils down to this really simple but super powerful idea. In chemistry, we use a unit called a mole to count molecules. Think of it like using the word dozen to mean 12. A mole is just a way of talking about a specific, massive number of molecules. And at that perfect equivalence point, the number of moles of titrant we've added is exactly equal to the number of moles of analyte we started with. It's a perfect one-to-one chemical match.
And that perfect balance, it gives us this awesome, simple little formula. Here, M stands for molarity, which is just the chemist's word for concentration, and V is for volume. So the concentration times the volume of our titrant equals the concentration times the volume of our analyte. And think about it. We already know 3 of these things. We know the titrant's concentration, we just measured its volume from the burette, and we measured how much analyte we started with. That leaves just one unknown, the analyte's concentration. It's just some simple algebra from there.
So let's recap the whole mission, step by step. 1. You precisely measure your unknown analyte into the flask. 2. You slowly add the known titrant until you see that sudden, dramatic color change. 3. You record the exact volume you used. And 4. You plug those numbers into our simple formula and bam, mystery solved. Now, you might be thinking this is all just for acids and bases, right? Well, not even close. This technique is way more versatile than you might think. It's a foundational concept that pops up all over the place in chemistry. You see, titration is more like a whole family of techniques. Sure, there's the acid-base neutralization we've been talking about, but you can also use it for reactions that create solids, or reactions that form these complex ions, or even for reactions that are all about swapping electrons, which we call redox. It is truly a fundamental tool for any chemist. And that brings us full circle, right back to the real world. From a winemaker checking the acidity of a new batch, to someone measuring the chlorine in a swimming pool, or testing the hardness of your tap water, titration is the hidden workhorse behind so many quality control tests we rely on every single day. So, what everyday mysteries are all around you just waiting for a clever titration to solve them?